Hello, I'm Essay, your AI essayist. Please note that all content, audio and video in this presentation are AI generated. As AI can sometimes produce inaccuracies, I encourage you to verify any factual information presented. With that in mind, let's begin.
The late 19th century witnessed a crisis in geometry's foundations. Euclid's Elements, for centuries the bedrock of geometric knowledge, revealed logical fissures, unstated assumptions regarding point ordering and the problematic method of superposition, and reliance on visual intuition rather than rigorous proof undermined the system's purported completeness. The emergence of consistent non-Euclidean geometries further complicated matters, challenging Euclid's axioms' unique status as a description of space. David Hilbert's 1999 Grundlagen der Geometrie offered a definitive response, revolutionizing the field. Hilbert's approach was radically novel. He established a purely formal axiomatic system. Point, line, and plane became undefined terms. The properties flowed solely from the axioms themselves. This abstract approach, famously illustrated by his tables, chairs, and beer mugs analogy, separated geometry from its intuitive spatial interpretation. Hilbert meticulously structured his axioms into 5 groups. Group I, incidence, defines fundamental relations. A line contains at least 2 points, a plane contains at least 3 non-collinear points, and so on. These axioms lay the groundwork, outlining connections between points, line, planes without assuming any geometric properties beyond it. Group and order introduces the crucial concept of betweenness. Instead of relying on visual intuition, Hilbert formalized betweenness through axioms. Pasch's axiom, a critical element, states that if a line intersects one side of a triangle, it must intersect another side, unless it passes through a vertex. This elegantly captures a spatial relationship without invoking visual interpretation. Group II, congruence, rigorously defines the equivalence of segments and angles. Euclid's reliance on superposition, intuitively moving figures, act formal justification. Hilbert replaced this with axioms precisely defining congruence, establishing a purely logical framework for geometric equivalence without relying on spatial operations. Group or parallels presents a formal version of Euclid's 5th postulate. This axiom, stating that through a point exterior to a line, only one parallel line can be drawn, is pivotal. Its independence from other axioms fetch a question addressed by Hilbert's subsequent Group V, continuity, encapsulates the Archimedean axiom, precluding non-standard magnitudes. Fundamentally, this axiom ensures geometric magnitudes can be compared by repeatedly adding a unit segment. This allows the formalization of the geometric continuum to align with the properties of real numbers, completing the link between the abstract axiomatic system and our intuitive understanding of geometric space. The axiom of completeness ensures the geometric continuum is isomorphic to the real numbers, consolidating the system's inherent continuity. Hilbert's work was directly influenced by Moritz Pasch's 1982 Vorlesungen über neue Geometrie, which highlighted the necessity of rigorous axiomatization, and Giuseppe Peano's formal axiomatization of arithmetic, providing a model for Hilbert's approach. The influence of Pasch is particularly apparent in Group II, order, where the explicit inclusion of Pasch's axiom marks a significant departure from Euclid and embraces the need for explicit logical steps. The direct applications of Hilbert's Grundlagen were immediate. It provided a rigorous foundation for geometry, removing the ambiguities and logical gaps of Euclid. This allowed for a deeper and more precise understanding of geometric concepts, facilitating clearer proofs and enhancing the logical security of geometric theorems. Mathematicians could now confidently construct geometric arguments based on clearly defined rules, eliminating reliance on visual perception and intuition. The first few axioms, for instance, build a logical structure from solely undefined terms and relations. In simplifying this shift towards rigorous logical deduction, the axioms themselves become the objects of study, their consistency and independence subject to logical investigation. The Grundlagen profoundly impacted subsequent developments. Hilbert's metamathematical approach, moving beyond axiomatics to analyze the system itself, profoundly impacted 20th century mathematics. His work directly influenced the development of metamathematics and the Hilbert Program, a project that sought to formalize all of mathematics, ensuring the consistency of foundational systems. Kurt Gödel's incompleteness theorems, a monumental achievement in the field, arose as a direct response to the objectives and ambition of the Hilbert Program. Furthermore, Alfred Tarski's proof of the decidability of elementary geometry, an achievement aligned with the broader ambitions of Hilbert's project, stands as another instance of the Grundlagen's enduring influence. Hilbert's work facilitated a foundational shift. separating mathematical truth from physical intuition and establishing the formalist axiomatic method as the dominant paradigm. Hilbert's Grundlagen der Geometrie, published in 1899, represents a pivotal moment in the history of mathematics. Its significance transcends the mere axiomatization of Euclidean geometry. It inaugurated a new era of metamathematical inquiry. Prior axiomatic systems, while rigorous, lacked a critical self-awareness. Hilbert's work, conversely, subjected the axiomatic system itself to rigorous examination. A revolutionary step, the Grundlagen presented a complete axiomatic system for Euclidean geometry, meticulously partitioning axioms into 5 groups: incidence, order, congruence, continuity, and parallelism. These axioms, unlike prior attempts, were explicitly stated, independent, and complete. Hilbert meticulously defined primitive notions, points, lines, planes through their relations governed by the axioms, eschewing reliance on intuitive geometric interpretations. This formalistic approach, a deliberate departure from Euclid's reliance on diagrams and geometrical intuition, was a profound innovation. The core innovation, however, lay not solely in the axioms themselves, but in Hilbert's subsequent metamathematical analysis. He tackled the fundamental questions of consistency and independence, questions largely ignored by his predecessors. He demonstrated the consistency of his axioms by constructing an arithmetic model. Points were represented by ordered pairs x, y from a specific field, and lines by linear equations, showing that the axioms held true within this arithmetic model proved that if arithmetic was consistent, so too was Hilbert's geometric system. This brilliantly reduced the consistency of a complex geometric system to the consistency of a more fundamental arithmetic system, marking a momentous shift in mathematical thought. Hilbert's proof of the independence of specific axioms further solidified his metamathematical approach. He achieved this by constructing models wherein a chosen axiom failed, while the remaining axioms remained consistent. A prime example involved the parallel axiom. Hilbert created a model satisfying all axioms except for the parallel postulate, demonstrating its independence. This rigorous demonstration, unlike Euclid's attempted proofs, undeniably established the parallel axiom as an independent statement, incapable of derivation from the others. Similar demonstrations were provided for other axioms, solidifying the system's completeness. This metamathematical achievement possessed profound implications. It directly fostered the development of the Hilbert Program, an ambitious project aiming to formalize all of mathematics and prove its consistency. Hilbert's second problem, explicitly calling for such a consistency, proof for arithmetic, stemmed directly from the success of the Grundlagen's methodology. This ambitious program, though ultimately proven unattainable by Gödel's incompleteness theorems, nonetheless profoundly shaped 20th century mathematical research. Gödel's theorems, in fact, arose directly as a response to the Hilbert Program's ambition. Gödel demonstrated that any sufficiently complex formal system containing arithmetic will invariably contain true statements unprovable within the system itself, thus shattering the hope for a complete, consistent formalization of all mathematics. While a setback for the Hilbert Program, this was a monumental achievement that stemmed directly from the metamathematical paradigm established by Hilbert's work on geometry. Alfred Tarski's proof of the decidability of elementary geometry represents further validation of Hilbert's initial impact. Tarski's achievement, providing an algorithm to determine the truth or falsehood of any given geometric statement within the framework of elementary geometry, fulfilled a portion of Hilbert's grand vision. This demonstrates the ongoing, direct influence of the Grundlagen's methodology on subsequent mathematical work. In conclusion, the enduring legacy of Hilbert's Grundlagen der Geometrie lies not merely in its axiomatization of Euclidean geometry, a feat remarkable in itself, but in its paradigm shift toward metamathematical analysis. The work established the formalist axiomatic method and the rigorous scrutiny of axiomatic systems as the cornerstone of mathematical rigor. This fundamentally reshaped the landscape of 20th century mathematics, separating mathematical truth from sheer physical intuition and charting a course toward a deeper understanding of the foundations of mathematics itself. Its influence reverberates through the work of Gödel and Tarski, standing as a testament to its foundational impact.
We really appreciate you tuning into this AI-powered presentation. Our goal is to push the boundaries of AI in content creation, and your input is invaluable. If there's a particular subject you'd like to see us tackle next, or if you have suggestions on how we could fine-tune our AI's creative prompts, please don't hesitate to leave your ideas in the comments section. We're excited to bring you more unique content very soon.